This is Chapter 11, Section 7, where we're going to talk about the reactions of acids and bases. One of the most common acid reactions is between the gastric acid produced by the lining of your stomach and the food that you eat. The gastric acid helps to break down the food until it reaches a low pH and gets it ready for digestion. In this section, we're going to learn how to write balanced equations for different reactions of acids with metals, with carbonates and bicarbonates, and neutralization reactions between acids and bases. We're also going to learn how to calculate the molarity or volume of an acid from titration experiment. When we're dealing with the Arrhenius or the Bronsted-Lowry definitions of acids, we generally think about them reacting with bases to neutralize them. But acids can also undergo other kinds of reactions that don't quite fit into this category. For instance, I mentioned previously that acids can corrode or dissolve some metals. The result of this kind of reaction is a salt and hydrogen gas, H2, and this is actually a reduction oxidation, not a typical acid-base reaction. Metals can also react with carbonate or bicarbonate ions, and they produce a salt, carbon dioxide gas, and water as a result. This is actually a kind of acid-base reaction, but the details are a little different than a typical neutralization, so we consider it a special case here. And last, of course, we do have the typical acid-base neutralization, which produces a salt and water. Remember that in chemistry, the term salt refers to any ionic compound that does not contain hydrogen ions or hydroxide ions. Here we see two examples of acids reacting with metals to produce hydrogen gas and what's called a metal salt. In the first example, we have solid magnesium, which is reacting with a solution of hydrochloric acid, and it's producing a solution of magnesium chloride, the metal salt, as well as bubbles of hydrogen gas, which typically escape into the atmosphere. We've actually seen this reaction in the laboratory a few times, where you can visualize the bubbles which are coming off the surface of the metal as it dissolves into the acid. What's really going on here is that the metal, which is neutral at the beginning, transfers electrons to the positive hydrogen ions in the acid and allows them to form hydrogen gas. This leaves the metal as a positive ion, which then combines with the negative ions from the acid. This is what makes this a redox reaction. You have a transfer of electrons from the metal to the hydrogen ions, and in fact, it's a single replacement reaction. In the second example, we have an almost identical reaction, but there's a difference in the mole-to-mole ratios between the acid and the metal. We always need two hydrogens from the acid because we always need to form a hydrogen molecule which contains two hydrogens. In this case, we also need 2 moles of the metal because sodium only forms +1 ions, so we can't get 2 electrons out of a single mole of sodium. You need 2 moles of sodium to provide 2 electrons to the 2 moles of hydrogen in order to produce the hydrogen gas. And as a result, you also end up with 2 moles of the metal salt, which in this case is just typical NaCl. The next reaction type is between acids and carbonate-containing compounds, or hydrogen carbonate compounds, otherwise known as bicarbonate. The carbonate ion is CO3 2-, and the hydrogen carbonate or bicarbonate ion is HCO3 with a 1- charge. It's really just a carbonate ion that has an extra H+ ion attached to it. For both of these reaction types, you have the carbonate or the bicarbonate combining with an acid to produce a salt, CO2, and H2O, liquid water. For each case, the salt is formed from the positive ion in the carbonate or the bicarbonate and the negative ion from the acid. So in the case of calcium carbonate and hydrochloric acid, you end up with calcium chloride as the salt. Now you may have noticed that this reaction doesn't quite look like any of the fundamental reaction types that we learned at the beginning of the course. That's because it's actually a 2-step process. In the first step, you have calcium carbonate combined with hydrochloric acid in a double replacement reaction. The hydrogen ions from the acid combine with the carbonate, and the calcium ions from the carbonate combine with the chlorides from the acid. So you end up with calcium chloride, which is the salt that we knew we were going to get, plus hydrogen ions combined with carbonate to form carbonic acid, H2CO3. Now, carbonic acid is actually what you get when you dissolve CO2 in water. In fact, there's an equilibrium between carbonic acid, CO2, and liquid water. So what happens in this reaction is that as you produce carbonic acid, a small amount of it is converted into CO2, which then escapes into the atmosphere, tilting the equilibrium further towards the carbon dioxide side. The carbonic acid, in this way, gets rapidly used up and effectively decomposes into CO2 and liquid water. So instead of there being carbonic acid at the end of the reaction, it's all broken down into those two components. This might also help you understand why the mole factors are different in a bicarbonate reaction. With a bicarbonate compound, the carbonate ion already has an H+ with it, and so you only need 1 mole of acid to provide 1 mole of hydrogen ions to complete the carbonic acid formula of H2CO3. So with carbonates, you need twice the moles of acid for every carbonate, but with bicarbonates, you only need the same number of moles of acid. And finally, we have a typical acid-base neutralization reaction. Here, the products are a salt and water. The salt is formed from the positive ion from the base and the negative ion from the acid. The water, of course, is formed from the hydrogen ions in the acid and the hydroxide ions in the base. In fact, the reaction between hydrogen ions and hydroxide ions to form liquid water, H2O, is the driving force behind all of these reactions. What that means is that we can actually think of acid-base neutralizations as double replacement reactions, where we begin with aqueous solutions of the acid and the base, in other words, individual ions separated from one another. As the reaction proceeds, the hydrogen ions combine with the hydroxide ions and produce liquid water. The other ions, the negative ion from the acid, in this case chloride, and the positive ion from the base, in this case sodium, are really spectators. They're not affected by the reaction. They don't necessarily combine together because they're still separate ions in solution afterwards. So even though we call this a salt, it's really dissolved ions. And so those can be crossed out because they're the same on both sides. Once you cross out those spectator ions, then you're left with the reaction between hydrogen ions and hydroxide ions to create liquid water. So again, this is the driving force and the net ionic equation for virtually every acid-base neutralization. Neutralization equations can be balanced the same way that we've balanced every other equation in this course, element by element. But it's actually a lot easier if you think about balancing the number of hydrogens in the acid with the number of hydroxides in the base. Since you always need a hydrogen to combine with a hydroxide to create water, these are the ratios that the substances need to be in. In this example, we have solid magnesium hydroxide and nitric acid. So to write the balanced equation for this, we first have to figure out the chemical formulas for these substances. For magnesium hydroxide, we're dealing with magnesium ions, which are Mg2+, and hydroxide ions, which are OH-. In order to balance the 2+ charge in the magnesium, we're going to need to take 2 hydroxides. And so the formula for magnesium hydroxide is MgOH2, where the OH is in parentheses. For nitric acid, we also need to understand the naming convention of acids. The ic acid means that this actually came from the nitrate ion, which we should know or look up in our table of polyatomic ions and find that it's NO3-. So to make this into an acid, you would combine it with hydrogen ions. Since the hydrogen ion is +1 and the nitrate ion is -1, the formula for nitric acid is just HNO3, one of each. Now that we know that these are our formulas, we can combine them together on the reactant side of an equation. We can take MgOH2 plus HNO3, and we're going to end up with a salt formed from the positive ion from the base and the negative ion from the acid, which would be magnesium nitrate. One way to balance it would be to figure out the formula for magnesium nitrate and then use those ratios to figure out the ratios of the reactants. In this case, though, what I'm going to do is break down the base and the acid into ions and show you how balancing the ions can help you to figure out what the products are. So we already saw, in fact, that magnesium hydroxide is one magnesium ion and two hydroxides. So we can use that picture right up there. For nitric acid, we saw that a mole of nitric acid is just 1 mole of hydrogen ions and 1 mole of nitrate ions. So when we want to combine acid and base, we have to make sure that every hydroxide in the base can be matched up with a hydrogen in the acid. In this case, we have too many hydroxides in the base, so we need to take another mole of the acid. I can't just arbitrarily add another hydrogen ion. I have to add a whole mole of nitric acid, which means I also get another mole of nitrate ions. That provides enough hydrogen ions to match up with both of the hydroxides from magnesium, and we find that we've created in this process magnesium nitrate formed from 1 magnesium and 2 nitrates, as well as 2 water molecules. Don't forget that since we took 2 nitric acid moles, we have to put a 2 in front of the formula for nitric acid. This is how you can balance every acid-base neutralization reaction. Make sure that the number of hydroxide ions in the base equals the number of hydrogen ions in the acid. If they don't match, then add a coefficient so that they do. Let's take a look at another example like this. Here we have a reaction between aluminum hydroxide and sulfuric acid, H2SO4. Since we need to balance the number of hydroxides in the base with the number of hydrogens in the acid, we should start by breaking these compounds down into their individual ions. In aluminum hydroxide, you have an aluminum ion, which is always 3+, and 3 hydroxides, which are each OH-. In the sulfuric acid, you have 2 hydrogens, 2 H+ ions, and a sulfate, SO4 2-. We can see that that's enough hydrogens to balance 2 of the hydroxides from the aluminum hydroxide, but we have 1 more hydroxide that we need to account for. To neutralize that hydroxide, I have to add more hydrogens, but since I'm only adding acid to get my hydrogens, I have to add a whole H2SO4 to the reaction. In other words, 2 hydrogen ions and another sulfate ion. This is going to give me 1 more water because it neutralizes that last hydroxide, but the problem is now I have too many hydrogens. So in order to get more hydroxides to neutralize that hydrogen, I have to add another aluminum hydroxide mole, which is another aluminum ion, and 3 more hydroxide ions. This, of course, neutralizes that last hydrogen from the second mole of H2SO4, but we now have 2 moles of hydroxide. And so we have to add 1 last mole of H2SO4 in order to balance those hydroxides. So what we end up with, if we look at what we added 2 moles of aluminum hydroxide, so I put a 2 in front there, and 1, 2, 3 moles of sulfuric acid, so I need to put a 3 in front there. Then I have to look at what my products are. Well, the easiest product is to just count the number of water molecules I made. That's 1, 2, 3, 4, 5, 6 moles of water, which would be in the liquid state. And then we have to look at the other ions and see what we have. We have a compound that's going to be formed from 2 aluminum ions and 3 sulfate ions. And so this is really just aluminum sulfate, which is Al2 SO4 in parentheses with a 3 outside. That's aluminum sulfate. And this is going to be aqueous. We can double check to make sure that the aluminum sulfate formula is balanced. +3 from each of the aluminums gives you a +6 charge. -2 from each of the 3 sulfates gives you a -6 charge. And so that's balanced, and that gives you a neutral compound. And we can also just do one quick check and make sure that it's the lowest ratio, right? The 2 aluminum to 3 sulfates is the lowest whole number ratio that gives us this charge balance. And so we're fine. And typically, if you do it this way, by balancing hydroxides and hydrogens, the other components will automatically balance. The other ions involved will automatically combine and balance into the metal salt. One place you may have encountered acid-base neutralization reactions in everyday life is if you've ever taken an antacid. Antacids are substances that neutralize excess stomach acid, and so since they're neutralizing acid, we would more typically know them as bases. Most antacids are composed of hydroxides, usually either aluminum hydroxide or magnesium hydroxides, or carbonates. These hydroxides are not very soluble, these are not strong bases, and so the levels of hydroxide ions that they generate are not damaging to the intestinal tract, but they do serve to neutralize excess hydronium from the stomach acid. This table shows some examples of some common brand names for antacids like Amphigel, Mylanta, Alka-Seltzer, as well as the active ingredient in them. You can see most of them are metal hydroxides of some sort, although there are also some carbonates involved. Notice that none of these are strong bases. A strong base can be just as dangerous or caustic as a strong acid, and so it's something that you would definitely want to avoid ingesting at all costs. This brings us to the common laboratory technique called an acid-base titration. In chemistry, a titration is a way to sort of experimentally balance the two reactions in a chemical equation. You have a solution with a known concentration, and you carefully add it to a solution of unknown concentration. By carefully adding it and measuring the volume it took to complete the reaction, you can then calculate the unknown solution from the known solution. This requires you to know the exact chemical equation between the two substances and very carefully control your concentrations and the volumes measured for both substances. There are a few different kinds of titrations that can be performed, but the most common is an acid-base titration. In an acid-base titration, like any titration, you need to be able to visualize where the reaction ends or where the two substances are completely balanced. The way this is done in acid-base titration is by using a pH indicator that changes color when the pH of the solution changes rapidly, either from acid to base or base to acid. This series of images shows you an overview of the titration process. You begin with your unknown solution in the flask and a known solution in the burette above. The burette allows you to dispense a precise volume of the known solution into the flask with the unknown solution. You also need an indicator in the unknown solution, which will go through some sort of visual change as the two substances react with one another, as you can see in the middle picture. The point of the indicator is that once the reaction is complete and the amount of the known substance has completely balanced the amount of the unknown substance according to the chemical equation, some property of the solution will change such that the indicator will undergo a permanent visual change. So let's take a look at each of these steps in more detail. We begin the titration with our unknown solution in the flask and the known solution in the burette above it. In this example, the acid is our unknown solution, meaning we know the acid, but we don't know the concentration of it. Even though we don't know the concentration, we do need to precisely measure the volume of acid in the flask, because we're going to need that for later calculations. For the base, we do know the concentration. This is considered our known solution in the burette. And the burette allows us to dispense a very precisely controlled volume of the base into the flask. We also need an indicator in the flask, which is going to allow us to visualize the endpoint of the reaction. For an acid-base neutralization, we need a pH indicator, which will change color depending on the pH of the solution. In this example, we're going to start with an acidic pH in the flask, and it's going to change to a neutral or basic pH as we add the base to it. At the exact moment that the base fully neutralizes the acid in the flask, the pH is going to rapidly change from low to a pH of exactly 7, if we can match it at the exact neutralization point, and then rapidly go above 7 with each additional drop of base. So what we want is an indicator that'll be one color, an acidic solution, and another color at a neutral or basic solution. Phenolphthalein fits this bill pretty well because it's clear in acidic solution and it turns bright pink when it reaches neutral or basic pHs. The endpoint for an acid-base titration occurs when the moles of hydronium exactly balance the moles of hydroxide. Now, you may have seen this in some sources or videos as the moles of acid being exactly equal to the moles of base, but this isn't actually true. It really depends on the mole coefficients in the chemical equation. So the moles of acid are balanced by the moles of base according to the ratio from the chemical equation. The ions themselves will always be exactly equal because you need one hydronium plus one hydroxide to produce neutral water. But each acid or base may contain one or more of the relevant ions, and so the ratio between the acid and base in the equation is not always going to be 1-to-1. You do need to account for that mole factor in your calculations. Either way, once you reach the endpoint and the hydronium exactly neutralizes the hydroxide, you see a visual color change in the indicator because the pH rapidly changes, and so you get this pink color in the case of phenolphthalein, which persists. At this point, the first point where you see a pink color which doesn't fade away, you've exactly reached the endpoint, and you know the precise volume of the known solution which has neutralized the given amount of acid in the flask. Now that you've determined the exact volume of the known solution, you can calculate the moles of the known solution. Since you know the concentration of the base in the burette, and you know the volume that you just dispensed from the burette, you can simply multiply these two values together, assuming your volume is in liters, and that's going to tell you how many moles of base you added into the flask. The mole-to-mole ratio from the chemical equation can then be used to figure out the number of moles of acid. In the simplest case, where it's a 1-to-1 ratio, then the number of moles of the base added is exactly equal to the number of moles of acid that must have been in the flask to begin with. Then you can calculate the concentration of the acid that you started from by taking that number of moles and dividing it by the initial volume of the acid that you started from. The concentration, again, equals the number of moles divided by the volume in liters. Hearing it explained or even doing the titration yourself is a lot different from going through the calculation. So let's do an example where we analyze the molarity of an HCl solution using a known concentration of sodium hydroxide. In this question it says, what is the molarity of an HCl solution if 18.5 milliliters of 0.225 molar sodium hydroxide is required to neutralize 0.0100 liters of the acid HCl. And it even gives us the balanced chemical equation between HCl and NaOH, which in this case is just a 1-to-1 ratio, which keeps things simple for this example. At first, this may seem like a new or confusing question type, but in fact, it's consistent with what we learned back in Chapter 9 for solution reactions. What we have is a known solution of sodium hydroxide, and we're trying to calculate something about an unknown solution of hydrochloric acid. So we can start with our known solution here on the left, and we want to end up with our unknown solution here on the right. So we can take the volume of sodium hydroxide, which they give to us, it's 18.5 milliliters, and we can use the molarity of sodium hydroxide, which they also give to us, to calculate how many moles of sodium hydroxide went into this reaction. Then we can use the mole-to-mole factor from the chemical equation to calculate how many moles of HCl must have been in this reaction. Now in Chapter 9, we would then have used the molarity of HCl to calculate the volume, but in this case it's a little bit backwards because we don't know the molarity, but we have figured out the volume from the titration procedure. So instead of using molarity to convert moles to liters, we just take the number of moles and we take the liters and we put those into the formula for concentration to calculate the molarity. So let's see how this works in practice. I'm actually going to solve this problem two different ways. The first way is going to assume that you understand the flowchart from the previous slide and that you need to begin with the known concentration of sodium hydroxide and end by finding out about the unknown concentration of HCl. So to do that, we would begin with the quantity of sodium hydroxide solution that we're given, 18.5 milliliters of sodium hydroxide solution. This needs to be converted into moles because this procedure requires us to relate mole quantities of the two substances. So we would use the concentration to convert volume to moles. This concentration, remember, 0.225 molar, really means you have 0.225 moles of sodium hydroxide per 1 liter. So I can use that as my conversion factor. I just have to remember to convert from milliliters to liters or vice versa. In this case, instead of using an additional metric conversion factor, I'm just going to express this denominator in milliliters. So I would end up with 0.225 moles of sodium hydroxide in 1 liter, which is really the equivalent of 1,000 milliliters. This ensures that my volume unit here can cancel my volume unit here. This is leaving me with moles of sodium hydroxide, which now needs to be converted into moles of HCl. So I would use the mole-to-mole factor from the chemical equation and take 1 mole of sodium hydroxide is equivalent to 1 mole of HCl. Again, because there's a 1 in front of HCl and a 1 in front of sodium hydroxide. This is a 1-to-1 ratio between the two. This is going to cancel moles of sodium hydroxide and leave me with now moles of HCl. In the solutions chapter, I would have then used the concentration of the solution to figure out the liters that I need or something like that. But in this case, like I said, it's somewhat backwards. We know the volume and we want to figure out the concentration. But once I know the number of moles of HCl, I can just figure out the concentration by dividing it by the volume, 0.0100 liters. Right? On top is just a 1 because all I'm doing is dividing by the volume. This is already expressed in liters, so I don't need to change that. And so this would be our final answer. We would end up with moles of HCl divided by liters, which is the molarity concentration. So 18.5 times 0.225 divided by 1,000 times 1 over 1 divided by 0.01. Put all that together and you get 0.416, keeping just 3 significant figures because of the 3 significant figures in our measurements. And so this is the final answer for the concentration of the HCl solution, 0.416 molar. The second way to solve this problem is backwards from the previous way, but sometimes it can help to start from what you know you're trying to calculate and then work your way backwards to see what you need at each step. So the question is directly asking, what is the molarity of an HCl solution? So we know that we should be using the formula for molarity. Molarity, as a measure of concentration, is equal to the number of moles divided by the volume in liters. For HCl, this is going to be the moles of HCl divided by the volume of the HCl solution in liters. Now, they gave us the volume of the HCl solution in liters. They told us that it's 0.0100 liters. And so the only thing that we really need to find now is the moles of HCl. We know that this titration process balances the moles of one substance versus the moles of another according to the chemical equation. So we can tell from the coefficients in the equation that 1 mole of HCl exactly neutralizes 1 mole of sodium hydroxide. What this means is that 1 mole of HCl equals 1 mole of sodium hydroxide. Or in fact, any number of moles of HCl equals the number of moles of sodium hydroxide. So in order to get moles of HCl, we actually have to calculate moles of sodium hydroxide. How do we calculate moles of sodium hydroxide? Well, they tell us 2 things about the sodium hydroxide solution. One, that its concentration is 0.225 molar, and the other is that its volume is 18.5 milliliters. Again, using the molarity concentration formula, we can say that the molarity of a solution equals the moles divided by the volume in liters. Now, whereas this first usage of the molarity formula is for the HCl solution, this second one is for the NaOH solution. And so we need to put in the molarity that we know of for the NaOH and the volume that we know of for the NaOH in order to calculate moles of NaOH. In other words, we're rearranging this equation to solve for moles of NaOH by taking the volume in liters and multiplying it by the molarity. This means that we have to take the volume which is given to us in milliliters and convert it to liters by dividing by 1,000. So you get 0.0185 liters of solution. And so that's what goes into this first part here, 0.0185 liters. And then our concentration is given to us as 0.225 molar, or 0.225 moles of sodium hydroxide per liter. The liter unit cancels, and we end up with a value of 0.00416 moles of NaOH. This is the moles of NaOH that we were looking for because it's going to be equal to the moles of HCl, and so really it's also going to go into the numerator here. And so the moles of HCl, the same as the moles of NaOH, is 0.00416 moles. You divide that by 0.01, and you end up with a molar concentration of 0.416 molar. This is the same answer that we got last time. Again, which method you use doesn't really matter. It just depends on which one makes more sense to you. If you understand the flow chart and working from your known to your unknown, then do it that way. If it makes more sense for you to start at the end and figure out what it is that you're looking for and work backwards, then you should use that way. Let's do a somewhat more difficult example using the first method. So here the question says, what is the molarity of an H2SO4 solution if 25.5 milliliters of 0.438 molar sodium hydroxide is required to neutralize 0.0250 liters of sulfuric acid, H2SO4? Luckily, they give us the balanced equation between these two substances. 1 mole of sulfuric acid neutralizes 2 moles of sodium hydroxide because each mole of sulfuric acid has 2 hydrogen ions in it. This produces sodium sulfate and 2 moles of water, but we're not really concerned with the products, more the relationship between the acid and the base here. So starting from the known substance, the base, we have 25.5 milliliters of the base solution, and we're going to multiply that by the concentration, which allows us to convert between liters and moles. 0.438 molar equals 0.438 moles per liter, which is really 0.438 moles of sodium hydroxide per 1,000 milliliters. Again, we're using the quick conversion of 1 liter to 1,000 milliliters to account for the fact that our volume is given to us in milliliters. So we want to cancel that unit out. This is going to leave us with moles of sodium hydroxide. But now we need to figure out how many moles of sulfuric acid that really is. From the 1 to 2 ratio here, we know that we want moles of sodium hydroxide in the denominator, and so that's where the 2 is going to be, because the 2 is in front of sodium hydroxide. In the numerator, we want moles of sulfuric acid, H2SO4, and that's just a 1, so that will be a 1. This moles of sodium hydroxide cancels the denominator unit here, and so we're ending up with moles of sulfuric acid at this point. And again, if you recall the concentration formula, the molarity of the sulfuric acid is going to be the moles of H2SO4 divided by the volume, which is 0.0250. So we can just take this value and divide it by that volume in liters. Altogether, this would give us our answer, which would be 0.223 molar sulfuric acid, or 0.223 moles per liter of sulfuric acid, H2SO4. You can see the only difference between this problem and the previous one is in the 1 to 2 mole to mole factor between the sulfuric acid and the sodium hydroxide. So it's very important to take that into account and not just assume that the number of moles of acid is going to be equal to the number of moles of base.